welcome to this problem walkthrough. Today, we'll explore problem number 571, find median given frequency of numbers. In this session, we'll review the problem, analyze different approaches, and focus on the brute force solution. Let's dive in. Specifically, for a row like number_i, frequency_i, number_i is the number, and frequency_i is how many times that number appears. In this problem, you are given a 2D array called data. Each row in this array represents an integer and its corresponding frequency. The array is guaranteed to be sorted in ascending order by the numbers themselves, which simplifies the process of analyzing the data. Your task is to determine the median of the numbers represented by this frequency list. Now, the median is defined as the middle value in an ordered list of integers. If the total number of integers is even, the median will be the average of the two middle values, but for this problem, you are required to round that average down to the nearest integer. Let's also quickly review the input and output formats. The input is a 2D integer array, where each row specifies a number and its frequency. The output will be a single integer representing the median of the expanded list of numbers. Let's look at the first example to better understand the problem. The input is 1, 2, 2, 3, 3, 1. Here, the number 1 appears 2 times, the number 2 appears 3 times, and the number 3 appears once. Expanding this frequency list results in 1, 1, 2, 2, 2, 3. To find the median, we locate the middle value of this ordered list. Since there are 6 elements, the two middle values are the third and fourth elements, which are both 2. Taking the average of these two values gives us 2 plus 2 / 2 equals 2. Since the average is already an integer, there's no need to round down. So, the median of this frequency list is 2. Now consider the second example where the input is 1, 1, 2, 2, 3, 3. Here, the number 1 appears once, the number 2 appears twice, and the number 3 appears 3 times. Expanding the frequency list gives 1, 2, 2, 3, 3, 3. To find the median, we again locate the middle values. Since there are 6 elements, the two middle values are the third and fourth elements, which are 2 and 3. Taking the average of these two values gives 2 plus 3 / 2 equals 2.5. However, because the problem requires us to round down, the median becomes 2. Finally, keep in mind the constraints and edge cases. For example, if there's only one number with a frequency of 1, the median is simply that number. When the total frequency is even, ensure the two middle elements are correctly averaged and rounded down. These constraints ensure the problem can handle large inputs efficiently while maintaining accuracy in the results. To tackle this problem, we considered two main approaches. The first is the brute force method, which is quite straightforward. Here, we explicitly construct a sorted list of numbers based on their frequencies. For each pair of values in the input data, we append the number to a list multiple times according to its frequency. Once the list is fully constructed, we can sort it, if necessary, and then calculate the median using standard methods. While this approach is intuitive, its major downside is inefficiency. Constructing the list has a time complexity proportional to the total number of elements generated, which can be enormous if even one number has a very high frequency. This makes it impractical for large datasets. On the other hand, the optimized approach avoids this inefficiency by focusing on cumulative frequencies rather than building the full list. The median in this case is determined by the middle position or positions in the overall order. By calculating cumulative frequencies as we process the data, we can pinpoint the range containing the median without ever explicitly constructing the list. This drastically improves performance, especially for larger inputs, reducing the time complexity to linear in terms of the number of data elements. This method not only streamlines the computation but also avoids memory overhead, making it far more scalable. Given the limitations of the brute force method, we chose the optimized approach for its clear advantages in both efficiency and scalability. Constructing a full list, as required by the brute force method, becomes infeasible for large datasets due to high memory usage and excessive computation time. The optimized approach, however, achieves the same goal with a single pass through the data and minimal additional space, making it a much better choice for real-world scenarios. When comparing the two, the brute force method is simpler to implement and easier to understand initially, but its inefficiency makes it unsuitable for larger inputs. In contrast, the optimized approach is highly efficient, handling large datasets with O(n) time complexity and constant additional space. The only trade-off is that it demands a stronger grasp of cumulative frequency calculations and median determination. The key insight here is recognizing that the median is tied to specific positions in the cumulative frequency, rather than requiring the explicit construction of a full sorted list. This realization allowed us to completely sidestep the inefficiencies of the brute force method, leading to a solution that is both elegant and practical. To solve this problem, we start by understanding the input structure. The input is a list of pairs, where each pair consists of a number and its frequency. For instance, a pair, number_i, frequency_i, means the number_i appears frequency_i times. Our goal is to construct an output list, frequency_list, where each number is repeated according to its frequency. The first step in the algorithm is input validation. We need to ensure that the input is a valid list of pairs, where each pair contains exactly 2 integers. If this condition is not met, we handle the invalid input by either returning an error or an empty list. Additionally, we check that the frequency_i, is non-negative, since negative frequencies don't make sense in this context. Next, we initialize an empty list called frequency_list to store the final result. This list will be populated step by step based on the frequency of each number. Finally, we iterate through each pair in the input. For each pair, if the frequency is 0, we skip it since it doesn't contribute to the output. Otherwise, we use the extend method to efficiently add the number repeated frequency_i times to frequency_list. This avoids unnecessary loops and makes the operation more efficient. Using the extend method for appending multiple copies of a number is key to improving efficiency, as it directly handles bulk operations. Once all pairs are processed, the constructed frequency_list is returned as the output. This approach is straightforward and handles edge cases effectively. For example, if the input is empty, meaning data is an empty list, the output should also be an empty list. Similarly, when the frequency of a number is 0, that number is excluded from the result. One additional consideration is handling large frequencies. Since the output list size can grow significantly, it's crucial to ensure efficient memory usage. By carefully managing the input and output structures, we can avoid potential performance bottlenecks. The chosen data structures are simple yet effective. The input is a list of pairs, making it easy to iterate through each number and its frequency. The output, frequency_list, is a flat list that simplifies sequential access, which is ideal for most use cases. Now, let's analyze the time and space complexity of this algorithm. For the time complexity, the algorithm first iterates through all pairs in the input list. This takes O(n) time, where n is the number of pairs. For each pair, we extend the list based on the frequency. Extending the list for a single pair takes O, frequency_i, where frequency_i is the frequency of the current number. Therefore, the total time complexity is proportional to the sum of all frequencies across all pairs, which can be expressed as O(n) plus sum, frequency_i. In terms of space complexity, the primary space requirement comes from the output list, frequency_list. The size of this list is proportional to the total frequency sum, or O, sum, frequency_i. Since no additional data structures are used, the auxiliary space complexity remains constant at O(1). Let's walk through an example to clarify how the algorithm works. Given the input data equals 1, 3, 2, 2, 3, 1, we will process each pair to construct the output list step by step. Starting with an empty list, frequency_list, we process the first pair, 1, 3. Here, the number 1 has a frequency of 3, so we extend frequency_list with 1, 1, 1. The intermediate result is 1, 1, 1. Next, we process the pair, 2, 2. The number 2 has a frequency of 2, so we extend frequency_list with 2, 2. The list now becomes 1, 1, 1, 2, 2. Finally, the pair, 3, 1, is processed. The number 3 has a frequency of 1, so we extend frequency underscore list with 3. The final result is 1, 1, 1, 2, 2, 3. For edge cases, if the input list data is empty, the output is simply an empty list. If a pair has a frequency of 0, that number is skipped. For large frequencies, the algorithm ensures efficient memory usage by leveraging Python's optimized list operations. Here's the Python implementation of the algorithm. It first validates the input, initializes an empty list, iterates through each pair, and extends the list based on the frequency. This ensures correctness, efficiency, and robustness in handling all edge cases. This Python implementation solves LeetCode problem number 571, find median given frequency of numbers. The goal is to find the median of a dataset represented as pairs of numbers and their frequencies. Here is a step-by-step explanation. First, we expand the dataset based on the given frequency pairs. Each pair, number, frequency, indicates that the number appears frequency times. We use a loop to iterate through each pair, and for each number, we extend the frequency underscore list by creating a list of frequency copies of number. This step ensures that the dataset is correctly constructed with all numbers in their appropriate frequencies. Next, we sort the frequency underscore list. Sorting is necessary because we need the data in ascending order to calculate the median. The sorting operation has a time complexity of O, n log n, where n is the total number of elements in frequency underscore list. After sorting, we compute the median. If the length of the frequency underscore list is odd, the median is the middle element, which is accessed using integer division, and //2. If the length is even, the median is the average of the two middle elements. This is calculated by finding the elements at indices n//2 1 and n//2, summing them, and dividing by 2. This solution is concise and handles edge cases such as empty input. The function will simply return an error if data is malformed or contains invalid frequencies. The implementation has a time complexity dominated by the sorting step, making it efficient for most practical use cases. This approach ensures correctness while being easy to understand and implement. To solve the problem of finding the median given the frequency of numbers, we start by expanding the frequency list. This involves iterating through the given data, where each pair consists of a number and its frequency. For each pair, we take the number and add it to a list as many times as specified by its frequency. This effectively converts the frequency representation into an expanded list of numbers. Once we have this expanded list, the next step is to sort it. Sorting ensures that the numbers are in ascending order, which is essential for finding the median. After sorting, we calculate the size of the list and determine the median. If the size of the list is odd, the median is simply the middle element. On the other hand, if the size is even, the median is the average of the two middle elements. This is done by identifying the two central indices, retrieving their values, and computing their average as a double. Finally, we return the calculated median as the result. This completes the implementation of the function. By following these steps, expanding the frequency list, sorting it, and calculating the median based on the size of the list, we ensure that the solution is both accurate and efficient for the given problem. The approach handles both odd and even cases seamlessly and leverages Java's built-in utilities, such as lists and collections, to simplify the implementation. Here we have a simple example where the input is a list of number frequency pairs, 1, 2, 2, 3, 3, 1. The first step is to expand this into a frequency list. To do this, we iterate through each pair in the input. For the pair 1, 2, we add 2 copies of 1 to the frequency list, giving us 1, 1. Next, the pair 2, 3 adds 3 copies of 2, resulting in 1, 1, 2, 2, 2. Finally, the pair 3, 1 adds 1 copy of 3, giving us the final frequency list 1, 1, 2, 2, 2, 3. Since the numbers were added in ascending order, this list is already sorted, so no further sorting is needed. Now that we have the frequency list 1, 1, 2, 2, 2, 3, the next step is to find the median. The length of this list is 6, which is even. For even length lists, the median is calculated as the average of the two middle elements. The middle indices are 2 and 3, corresponding to the values 2 and 2. Taking the average, we get 2 plus 2/2 equals 2.0. Therefore, the median of the frequency list is 2.0. This completes the first example. Moving on, let's look at a second example where the input list has an odd length. In this second example, the input is 5, 2, 3, 1, 6, 3. First, we expand it into a frequency list. The pair 5, 2 adds 2 copies of 5, giving 5, 5. Then, 3, 1 adds 1 copy of 3, resulting in 5, 5, 3. Finally, 6, 3 adds 3 copies of 6, which gives 5, 5, 3, 6, 6, 6. Now, we need to sort this list to arrange it in ascending order. After sorting, the frequency list becomes 3, 5, 5, 6, 6, 6. With this sorted list, we can calculate the median. The length of the list is 6, which is even. Again, for even length lists, the median is the average of the two middle elements. Here, the middle indices are 2 and 3, corresponding to the values 5 and 6. Taking the average, we calculate 5 plus 6/2 equals 5.5. So, the median of this frequency list is 5.5. In this final example, the input is a single number frequency pair, 10, 1. We start by expanding the frequency list. The pair, 10, 1, adds 1 copy of 10, resulting in the frequency list, 10. Since there's only one element, the list is already sorted. To find the median, we note that the length of the list is 1, which is odd. For odd-length lists, the median is simply the middle element. Here, the only element in the list is 10, so the median is 10. This example highlights how the process simplifies when the input has just one pair. From these examples, we can take away a few key insights. First, expanding the frequency list ensures that every number appears in the list according to its frequency in the input. This step is crucial for median calculation. Second, sorting the frequency list guarantees that the numbers are in ascending order, which is necessary to identify the middle elements. Finally, the approach to finding the median depends on whether the list length is odd or even. For odd lengths, the median is the middle element, while for even lengths, it's the average of the two middle elements. These principles apply to all test cases and ensure that the solution is both accurate and efficient. In this problem, the time complexity is determined by 3 key steps. First, we expand the frequency list. For each pair of a number and its frequency in the input data, we append that number to the list multiple times based on the given frequency. If there are k pairs in the input and the total of all frequencies is n, this operation takes n time because we're iterating through the frequencies and populating the list. Next, we need to sort the frequency list. Sorting a list of size n uses Python's timsort algorithm, which has a time complexity of n*log n. Finally, we find the median. If the list has an odd length, we simply access the middle element, which is an O1 operation. For an even length, we calculate the average of the two middle values, which is also O1. Since this step involves only constant time operations, it doesn't significantly impact the overall complexity. Now, when we consider the overall time complexity, the sorting step, which takes n*log n, dominates the process. This makes the total time complexity of the solution n*log n. On the space complexity side, there are 3 main contributors. First, the frequency underscore list requires space proportional to the total number of elements, which is n. Second, while Python's timsort is in place, it does require log en, auxiliary space for handling recursive calls during sorting. Finally, the input data storage, which is proportional to the number of pairs k, also contributes. However, since k is typically much smaller than n, this space is negligible compared to n. Combining these factors, the space complexity is mostly driven by the storage of the frequency underscore list, making it n. Looking at the overall space complexity, the most significant contributor is the frequency underscore list, which takes n space. Adding the log n auxiliary space for sorting, the total space complexity remains n. Now, let's analyze the best, average, and worst case scenarios. In the best case, even if the list is already sorted, we still need to expand the frequency list, which takes O, n, and the sorting step must still be performed, resulting in O, n asterisk log, n, time. For the average case, the complexity remains O, n asterisk log, n, as the sorting step dominates. In the worst case, the time complexity is again O, n asterisk log, n, because it depends solely on the size of the frequency underscore list, which is proportional to n. This consistency across all cases emphasizes the efficiency of our approach. When comparing this solution to a brute force alternative, a naive approach might involve calculating the median dynamically while expanding the frequency list. However, this would require repeated insertions into a sorted structure, resulting in a much higher time complexity of O, n squared. Our optimized approach, on the other hand, minimizes the time complexity by sorting the list only once after the expansion step, making it far more efficient. To justify the big O mathematically, expanding the frequency list contributes O, n, sorting the list contributes O, n asterisk log, n, and accessing the median is O, 1. Since the sorting step dominates, the overall time complexity is O, n asterisk log, n. Similarly, the space complexity is dominated by the storage requirements for the frequency underscore list, leading to a total of O, n. This balance between time and space efficiency highlights the effectiveness of the solution. When solving this problem, there are several common mistakes to avoid that can trip you up during implementation. First, it's crucial not to ignore edge cases. Scenarios like an empty input, a single element array, or even large frequencies can cause runtime errors or incorrect outputs if not handled properly. For instance, if the data is empty or contains something like 5, 0, your solution should handle these gracefully without crashing or producing invalid results. Next, be cautious about how you interpret the frequency values. Misunderstanding the frequency parameter as the number itself, rather than the count of occurrences, is a frequent mistake. Always ensure you thoroughly understand the problem statement. Another pitfall is inefficient sorting. Sorting the entire input unnecessarily, instead of focusing on the relevant data, can significantly increase time complexity. For example, if only the frequency matters, avoid sorting by both the number and the frequency. Finally, brute force approaches that explicitly construct large frequency lists can lead to memory issues, particularly for large input sizes. If a frequency is extremely high, like 10,000, this method can quickly become impractical, so always consider memory constraints in your solution design. Now, let's look at some optimization opportunities and interview strategies. One common inefficiency is not leveraging appropriate data structures like heaps or hash maps for frequency-based processing. These can make your solution both faster and more space-efficient compared to naive approaches. During an interview, it's also important to clarify the problem scope early on. Ask questions about edge cases, such as how to handle negative numbers, zeros, or extremely large values. This shows the interviewer that you're thorough in your analysis. Additionally, always optimize for the given constraints. For instance, if the problem specifies that frequencies are small, focus on minimizing unnecessary overhead by building the result incrementally rather than relying on intermediate data structures. Another critical aspect is balancing time and space trade-offs. Interviewers often evaluate whether you can justify your choice of approach, whether it's prioritizing efficiency with a heap or simplicity with sorting. Make sure to discuss edge cases proactively before coding to demonstrate your thought process. Many frequency-based problems also follow common patterns, such as sorting, using heaps, or leveraging hash maps, so developing a strong understanding of these techniques will help you adapt quickly in interviews. To deepen your understanding, it's helpful to explore related problems that share similar patterns. For instance, LeetCode 347, top k frequent elements, is a classic example that involves using heaps or sorting based on frequency. Similarly, LeetCode 451, sort characters by frequency, follows a comparable approach but involves characters instead of numbers. LeetCode 692, top k frequent words, adds a layer of complexity by combining frequency sorting with lexicographical order. Even problems like LeetCode 75, sort colors, though simpler, involve counting and sorting concepts that build intuition for frequency-based operations. When considering alternative approaches, brute force is the most straightforward. This involves explicitly constructing the result list by appending each number frequency times and then sorting the entire list. While simple to implement, this method becomes inefficient for large inputs due to its high time and space complexity. A more efficient alternative is a heap-based solution, where a max heap or min heap is used to extract elements based on their frequency. This reduces the need for full sorting and is particularly useful when only the most frequent elements are required. However, heap-based solutions require familiarity with heap operations and may be slightly harder to implement. Another highly efficient approach is bucket sort. Here, you use an array of buckets where the index represents frequency, grouping elements accordingly. This method is extremely fast, running in linear time, but can be slightly harder to conceptualize for beginners. Lastly, there's the hash map with sorting approach, where you count frequencies using a hash map and then sort the elements based on their frequencies. This method is easier to implement than bucket sort but slower due to the sorting step. Each of these approaches has its own trade-offs in terms of complexity and ease of implementation. Choosing the right approach depends on the constraints of the problem and your familiarity with these techniques. Understanding the advantages and limitations of each method will help you make well-informed decisions, whether you're solving problems on your own or during an interview. Great job making it to the end. We covered problem number 571, focusing on the brute force approach. Remember, this method is a starting point and helps build intuition for optimization. Keep practicing and exploring coding challenges. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!